Okay, we are going to look at problem number 5. So this is the first time we've seen a problem like number 5. So I'm going to teach this one to you. Okay? So again, as always, after we've read this, one of the first things you want to do is you want to look at what the information they've given you. So last time we were looking at graphs, now we are looking at a table. And I want to decide, what is this table? Is it a position function, a velocity function, or an acceleration function? In this case, right, this is they are giving us hours and people. So number of people is going to be a position, right? If I wanted to find the rate of change of those people, it would be a derivative. But in this case, our units are people. So this is a position function. Okay, let's see what we got here. So we've got these concert tickets, and they're sold going from time 0 to 9. They're being sold from time 0 to 9. And L of t gives us the number of people waiting in line. Okay. Also, let's see what else. This is kind of important, so I just want to point this out. This is twice differentiable. And what that basically tells us, by telling us that, one is they, of course, tell us that we can take the derivative twice, right? But it also means that it specifically means it's continuous. So it's L of t is continuous, and also L prime of t is continuous. Okay, so that's pretty important. And we might want to keep that in the back of our minds. So not only is this thing twice differentiable, but it's also continuous. So what do we got here? So use the data. So looking at part A, use the data in the table to estimate the rate at which the number of people in line was changing at 5:30. So we want to find basically the rate of change at 5:30. So I think you'd agree what we're really being asked to find is what is L prime of 5.5. Now, we are going to use this. Notice what they said. They're asking us to estimate, right? We can't give the exact value, but we can estimate. So think about what we're trying to find. We're trying to find basically the slope of the tangent line at 5.5. Well, I can't, again, without a function, I can't give the exact value, but I can say, hey, you know what? 5.5 is somewhere between time 4 and time 7, right? So what if I go and find the slope of the tangent line from time 7, well, time 4 to time 7, I'm just kind of writing this in the slope of a line form, right? So what I'm going to do is I'm going to find the slope of the tangent line from time 4 to time 7, and I'm going to say L prime is about that. Again, is it perfect? No, but it's an estimate, which is all they're asking for. So in this case, what do we get here? We get L of 7 is 150, L of 4 is 126, and 7 minus 4 is 3. So I get... Now, again, I do want to emphasize, you could leave it like this. I know it's a calculator question, so we might not. But I'm going to simplify this, and I get 8. Now, they did ask us to indicate units. So in this case, think about what's going on. We're taking, so on top, this is people. On bottom, this is hours. So it's people divided by hours. So let's do people divided by hours. Okay? Or people, I guess you could say people per hour, right? That makes a little more sense in this situation. Okay? That is the first one. By the way, just a quick note. Notice how they asked you to indicate units of measure. What that probably means, right? This is probably a 2-point question. So point number 1 would be for, your answer, one of these two things. Point number 2 is for this, right? For people per hour. In other words, let's say you had no idea how to do this, but you knew the units. You're like, I have no idea how to figure out L prime of 5.5, but I do know it's going to be people per hour. If you say, hey, people per hour, you don't know the number, but you put people per hour, you're probably going to get 1 point just for knowing the units. So be careful on that. But what that also means is if you forget the units, you're losing half the points on the problem. Assuming, of course, it's a 2-point problem. Let's move right along. So use a trapezoidal sum with 3 subintervals to estimate the average number of people waiting in line during the first 4 hours. So average number of people, this is an average value theorem, right? Average number of people. So we're taking people divided by time, so that's average value. So in other words, what we're really being asked to find is we are being asked to find our average value. So that's 1 over 4 minus 0 on the interval. Is it the first, did they say the first 4? Yeah, 0 to 4 of L of t dt, right? They're asking for the average value, okay? So how do we do that? Well, again, this is, we are estimating, right? So basically what we're trying to find is imagine, right? We could graph these points, right? We could have this, we could on a coordinate grid, we could graph these points, and then we could find the area underneath the curve, right? From 0 to 4. So I'm going to kind of do the same thing, but of course this is going to be using a trapezoid. So they want us to break this trapezoid. It's a trapezoidal sum into 3 subintervals. Now remember, when it's a trapezoidal sum, those intervals don't have to be the same. We're just using trapezoids to determine. So for example, one trapezoid will have a base from 0 to 1. Another trapezoid would have a base from 1 to 3, so 2 units. And then finally, a third trapezoid would be from 3 to 4, right? That's 3 trapezoids, and this base is 1. So let's go and do that. So what's going to be our answer? Our answer is going to be 1/4. Let's do the first trapezoid. Again, you don't have to get fancy, right? Find the value for each trapezoid. So again, our trapezoids are base times height. Well, sorry, the average of the bases times the height. So our bases are from 0 to 1, it's going to be 120 plus 156. And then our height, right, is 1. For the next trapezoid, so I just finished doing this trapezoid. Let's move on to the next trapezoid. For the next trapezoid, it's going to, again, be 1/2 the average of our 2 bases, so 156 plus 176. And then our height is from, what is that, 3 minus 1, or 2. And then our third trapezoid is going to be, what is it? It is 176 to 126, and it is going to be 4 minus 3, or 1. Okay? Again, this is fine. This is a number. You can leave it like this. But if you want to, you can plug this into your calculator. So I get, for this one, I've actually already done this on my calculator. So I get 155.25. Now, I know they didn't ask for it, but the units for the average value are going to be the same as the units of the original function. So this is people. They're asking for the average number of people. Okay? Again, you could have just left it like this. That would be fine. Let's move on to letter C. Now, letter C, I will tell you, it's not particularly hard, but it's kind of a long one. Okay? And well, let's go over what they're asking, then we'll I'll show you why it's kind of long. So, what is the fewest number of times where L prime must be equal to 0? So really what they're asking is, right, if you think about this, this is a twice differential function, and this is our position function, and they want to know basically when L prime must equal 0. So what they're really asking is things like, where does this thing have critical values, right? How many critical values must it have on the interval from 0 to 9? That's what it's really asking. So let's think about, where do we find critical values? Well, critical values occur when the derivative, in this case, L prime, changes from, since we're talking about L, let's talk about it in terms of L. So it's going to, critical values are going to occur when L changes from either increasing to decreasing or decreasing to increasing, right? Where L prime changes from positive to negative or negative to positive, okay? So again, when we want to find critical values, we take our derivative and we see where does it change sign. So how are we going to do that? So the first thing I'm going to do is I'm going to want to use mean value theorem here, and I'll show you why. So let's just kind of quickly go through. Notice, look at our y values here, our LT values. Notice how we're increasing from 0 to 3, we are increasing, right? But then notice what happens. From 3 to 4, we're decreasing. So I think you guys would agree there must be a critical value somewhere from 0 to 4, right? Because we go from increasing to decreasing. So that's 1. But then we go from 3 to 4, we're decreasing. 4 to 7, we're increasing. So somewhere on the interval from 3 to 7, there must be another critical value or a place where it equals 0. And then finally, from 4 to 7, we are decreasing. From 4 to 7, we're increasing, not decreasing. And then from 7 to 9, we are decreasing. Therefore, on the interval from, 4 to 9, there must be another critical value or a place where it equals 0. So we know there's 3, but how do we justify it, right? And this is kind of, like I said, this is kind of the hard part. So what I'm going to say is I'm going to be typing this a little bit just because this is a little bit longer one and I want to make things a little bit neater for you guys. So I'm going to say we were told L of t is twice differentiable, right? So we were given that, which means mean value theorem, MVT, applies, right? So in order for mean value theorem to apply, the function has to be differentiable and continuous, and obviously differentiability implies continuity. So the first thing I want to show is say, hey, look, mean value theorem applies, MVT applies, okay? So why is that important? Well, that's important because let's go start getting some values. Let's start using mean value theorem. So I'm going to say, let's look at that first interval. So that first interval where it's increasing. So it's increasing from 0 to 3. So let's see here. I'm going to try to. So let's see what we got. So I'm going to say L of 3 minus L of 0 over 3 minus 0 equals, what is that? 176 minus 120 over 3, which is, now the big thing is that it's positive. I'm going to go and give a number here, which this is a number, that's fine, but I'm going to go plug that into my calculator, and I got 18.667, okay? Now, what's important by that, right, is by mean value theorem, right, so by MVT, there must exist a C. I'm going to call this C1 because we're going to do this multiple times, so I just want to kind of differentiate. So there must exist a C1 such that not in F, L prime of C1 equals that number, 18.667. The big important part here is that it's positive, right? I want to show that it's changing from increasing here, right, positive, to then decreasing from 3 to 4 and back and forth. So whether you put the numbers there or not, that's up to you. I'm going to just use those numbers, a little more straightforward. Okay, then I'm going to say, hey, look, let's go from 3 to 4. So on 4 to 3, same thing, right? So what was 4? 4 was 126, 3 is 176, and that's going to be over 1. So that's going to be equal to negative 50. So I'm going to then say exactly the same thing. So, and this is going to get a little bit repetitive, and I apologize, but let's see if I can I cheat this to make it faster for you guys? I'm not doing this for myself. I'm not doing it to be lazy. I'm doing it for you guys. I really want to emphasize that, right? Let's see what I can do here. Watch, I am not going to make this any easier for myself. Let's see what we got here. So, that's pretty bad. Okay, so by MVT, there must be a point C2, right? such that f prime, or L prime, excuse me, L prime of C2 equals negative 50. So this is a big deal, right? I've already shown that there's one interval on 0 to 4. Now I have to still state it, but we can kind of see what's going on here. I'm kind of highlighting a few things. I'm highlighting, hey, look, there's got to be a place where the derivative is positive. There's got to be a place where the derivative is negative. Let's keep on going, right? Let's keep on going. So our next interval is going to go from, let's see, we just did 0 to 3, and then we did 3 to 4, so now we got to be going from 4 to 7, right? Let's double check, because, yeah, from 4 to 7 is increasing. So I'm going to say L of 7 minus L of 4 over 7 minus 4 equals, what is that? So that is 150 minus 126 over 3, and that's a terrible 3, equals 8. So again, same reasoning and same being cheap. Let's fit that in there. So let's see what we got here. So by MVT, right, there must be a C. This is our third C, such that L prime of C3 equals positive 8, right? So we've identified another place. And then let's see. It looks like we're on our last interval, right? Our last interval. So let me double check. Is it our last? We just went from 4 to 7. Now we're going to go from, 7 to 9. That's where it's decreasing, right? So now I'm going to say from L9 minus L7. 9, is it 9 minus 7? Yeah, 9 minus 7. That equals 0 minus 150 over 2, which is negative 75, right? So again, by MVT, the good stuff occurs. Okay? I'll get rid of that little 1 there. So by MVT, there must exist another C. Which one are we on now? C4? Such that, okay. Let me clean that up a little bit. So there must be where it equals negative 5. Okay, so we've established a couple things. Let's see, now we haven't finished, but we've established there's a place where the derivative is a positive number, where it's a negative number, where it's a positive number, where it's a negative number, right? So now what am I going to do? I'm saying the key here is, now what I want to say is, how do I know it equals 0, right? How do I know that just because it goes from 18.667, just because it goes from here, so 18.667 to negative 50, how do I know that it's positive? Well, I think you'd agree. Well, you'd say, well, hey, the function's continuous, right? And if it's continuous and 0 is in between these two numbers, then somewhere on that interval from here to here, right? From, what was it? From, we'll just call it the interval containing these two. There must be a 0, right? So you may or may not remember this, but there's a theorem for that. And that theorem is intermediate value theorem. So what I'm going to say here, and I'll type this out, I'm going to say, since L of t is twice differentiable. I could just say differentiable, right? I don't really need to say twice. Just being differentiable once is fine because it's continuous. Twice differentiable is just overkill. But let's just use their wording. Since L of t is twice differentiable, L of t is continuous. Continuous is continuous. So why is that useful, right? Why is that useful? Well, here's why it is. So what I'm going to say, again, I'll probably just type this out. So I'm going to say, let's see. How do we want to say this? So let me see, by the above, right? So by the above work, by the above on, it doesn't matter if we're closed or open. they ask us to do anything with closed or open? I don't think they did. So on, let's say, on 0 to 3, L, sure, I'm going to type L prime of T, L prime of C1, right? Actually, you know, let me just write this in my hand. This is kind of, I'm struggling here. Okay, what do we got? So what do we got? So I'm going to say, since, okay, actually, I apologize. Let's keep on going. So let's start with our first interval. So by the above, by our above work, by the above, on 0 to 3, L prime of C1 equals, what did we say it equals? 18.667. On 3 to 4, L prime of C2 equals negative 50, right? Since negative 50 is greater than or equal to 0, which is greater than or equal to 18 point. Let's say that again. Since negative 50 is less than or equal to 0, which is less than or equal to 18.667, by naming the theorem by IVT, there must exist a C on 0 to 4 such that L prime of C equals 0. And then I'm just going to end, right? So I'm given my general thought process. So I'm going to say this same, this same logic or this same thing applies on the intervals. So what other intervals does it apply to? So it applies to on the intervals from 3 to 7, right? Let's just double check it, right? From 3 to 7, because it goes from decreasing to increasing. So on 3 to 7 and 3 to 7 and looks like 4 to 9 and 4 to 9. Okay. You don't have to go. I know this was kind of a long one. I'm trying to keep it short. So we've kind of gone. So notice what we've done here, right? In part 1, we've established, right, that there's certain values that L prime must be equal to, right? It has to be equal to a positive here, negative, positive, negative. Then I'm using IVT to establish that, hey, look, because 0 is in between these two values, there must be a 0 on that, on that specific interval. Okay. Again, kind of a long one, but the nice thing is these other pieces are pretty short. Let's go on to the last one. This last one's actually really short. So what do we got here? For this last one, they want to know the rate at which tickets were sold on 0 to 9 is modeled by this function, where it's given in tickets per hour. So this is a rate of change, right? This is a derivative based on the model, how many tickets were sold by 3 p.m. This is really straightforward. All they're asking us to do, right, is they're asking us to take this thing, our function, and evaluate it at 3, right? So in other words, this equals this. And this is really a calculator question. So there is no, you don't have to show any work. You don't have to do anything. You just need to plug it into your calculator. I got for this one, I got 972.784, and they want it to the nearest ticket. So I'm going to say 973 tickets. Okay. That is question number 5.